Okay, so we obviously, solubility was a big part of our properties of compounds lab yesterday. Okay, it basically allowed us to perform the last two tests, but also told us whether material is soluble or not. Now, solubility means the degree to which something dissolves in something else. Okay, in technical terms, how much of a solute will dissolve in a solvent. Right. Okay. Most of the time, the solvent is going to be what material? Water. Okay. We call the water the universal solvent for a reason. Okay. I mean, not everything is soluble in water, but certainly lots of stuff is. And most of the time, when we're dealing with solutions, they are something dissolved in water. Right. Since not everything is soluble in water, we do have other types of solvents. Okay. Especially if we are dealing with like non-polar types of materials. Okay, like oil-based paints, things like that that you can't get off of your hand if you get them on with soap and water. Okay, so you would have to use something else like turpentine or bar sol, okay, or some other solvent that can dissolve those things because water can't. Okay. All right, so we're going to learn the terminology related to solubility. That's more than likely going to be a review for you. Okay, it's probably going to be stuff you've heard before. Okay, we're going to look at what's meant by the term polar molecule. Okay, if something is polar, what does that mean?
It's opposites.
Right, it has two distinct sides or two distinct opposites. Okay, like Earth is polar, it has a north and a south pole. Okay, a battery is polar, it has a positive and a negative pole. Okay, things like that. There's psychological terms, okay, about being like I don't know why they call it bipolar. The definition of polar is to have two sides. But, there's like bipolar disorder where people can become manic and then depressive, okay, and they can switch very quickly between the two. So it's basically talking about any object, material, person having two extremes, okay, or two sides, okay, or something like that. All right, so that's what polar means. So then if something is a polar molecule, it's going to have two distinct ends, right? And what that means is one end will be positively charged and the other end will be negatively charged, right? And we're going to look at the effects that can have on the behavior of those materials, especially water. And because if we think about it, water does a lot of stuff that is strange, okay? Most things, when they become a solid and they get colder, what do? They contract. What does water do? It expands. Okay. Now, that's true right at its freezing point. Once you have ice, the colder the ice gets, the more it contracts. Okay, it'll follow that pattern again. Okay, but water, because it's a polar molecule, actually expands as it freezes. You all know that if you've ever frozen a bottle of water and then tried to stand it on a counter. Okay, it expands out the bottom and makes the bottom all rounded out. Right? And the reason for that is, as water contracts, as all things do when it gets cold, it starts pushing positively charged ends together. And what do positives do to each other? They repel, right? So there comes this point where water is getting closer and closer and closer, and then all of a sudden, repulsion happens. And that's right at the point of freezing. Okay? So water actually takes up the least space at about 4 degrees Celsius. And below that, as it starts to crystallize, it actually expands. Okay? And then once it becomes a solid again, then it obeys kind of those same rules where it'll contract more as it cools after that. Okay, and lastly, understand that because it is a polar molecule, it has many important and unique properties that make life on Earth possible. Okay, so that's just one of the things. Okay, why is it important that water expands when it freezes? Why is that something that life depends on?
Everything in the ocean died, the ice would just go falling down.
Yeah. In fact, that would mean that most lakes would freeze from the bottom, which would mean they would freeze solid completely. Okay? Which would mean no aquatic organisms would be able to overwinter because there would be no liquid water. There would be a big chunk of ice with dead fish in it. Okay? Or any other aquatic organism. So the fact that ice is less dense than liquid water means that a protective layer of ice forms on the top of a lake or any other water body, okay, and liquid water can persist underneath. Everyone kind of follow me on that? So that's one of those things. Okay. We also know that water does some other strange things, like if you have a really cold drink, what do you notice about the condensation on the outside of the glass? Yeah, it can stick, right? Like it doesn't run down until the droplets get to it kind of too heavy to stick anymore, and then they fall down. Okay, that's due to the polar nature of water as well. Okay, it's a process known as adhesion. It's important for plants to be able to use that in order to transport water from their roots to their leaves. Okay, and water can actually stick to itself as well. You've seen that if you've like filled a cup or something just to the top, and then you can get it kind of slightly more than full because you get that kind of surface tension, okay, on the bubble, right? That's because water is a polar molecule and can actually form weak hydrogen bonds with itself, okay, forming that surface tension using a process called cohesion, okay, meaning it bonds to itself. Right? All of those are important things for plants, for animals, for all life on Earth to be able to thrive. All right, so those are the kinds of things we're going to look at today. But we'll start off with solubility. Obviously, some substances will dissolve easily and others will not. Okay, this is solubility. Okay, and on the back of your periodic table, and you can just have a quick look at that, there is a chart that tells you the solubility of some common ionic compounds in water at 298.15 Kelvin. Okay. We'll be talking about how that solubility chart works in a little bit here, okay, and how you can determine how soluble something is just using that chart. Okay. So a substance is said to be insoluble if it will not dissolve in another substance. Okay, so there's first terminology. Okay, the term insoluble means it will not dissolve. Okay, if a substance remains insoluble in a solid form, then we call it a precipitate. Okay, when we go and we do our chemical reactions lab in a couple of weeks, we're going to have a few times where we mix two liquids, or solutions, not liquids, two solutions together, and the result of the reaction will be a soluble form. Okay? And that solid will fall out of solution and collect on the bottom of the tube or whatever container we use to perform the reaction. Okay? So we'll see this thing essentially fall out, or precipitate, okay, out of the solution and collect on the bottom. So we call it a precipitate. Anything that falls out of something else is precipitation. Okay. All right, so precipitate, also important terminology. All right, so you can kind of see here we would have just a solution here on the left, okay, obviously just one visible part, but you can see here that we have some sort of insoluble material that is going to eventually probably settle to the bottom of that test tube, right, and then that would be called a precipitate. All right, a solution. Okay? A solution is any mixture containing a solute dissolved in a solvent. Okay? It can also be called a homogeneous mixture, or homogeneous, however you say it. Either way is fine. Okay? Okay? We're going to hear this term quite a bit, homogeneous or homogeneous. Okay? Just so you know, the prefix homo means how many parts? Same part, one part, okay? Homogeneous means that there's no difference, okay? It's all together. So, like milk is homogenized, okay? This is the kind you buy in the store is homogenized. The kind that comes out of the cow, it's not, okay? If you milk a cow and just leave that, it'll separate, okay? The cream will rise to the top, okay? Everything else will settle to the bottom, right? It has to actually undergo pasteurization in order to remain homogenized. Peanut butter. Same thing, you can buy homogenized peanut butter, that's the way most stuff is, but if you buy the organic stuff, it usually isn't, and it'll separate. There will be peanut oil on the top, okay, and all the other stuff on the bottom, and you have to stir it every time you're going to make something with it. Okay, so homogenized means to make it all one part and stay that way. Okay, so homogeneous means one visible part. Okay, if something is heterogeneous, that means it has many parts. Yeah, hetero means many or more than one. Okay, so two substances mixed together that do not dissolve, okay, can also be called a mechanical mixture. Okay, oil and water, okay, iron filings and sand. I can mix those things together, but obviously they don't dissolve in each other. Okay, if you go to Subway and get a sandwich, they put salt and pepper in the same shaker. I don't know why, but they do. Okay, and so it's a mechanical mixture. I'm not making pepper dissolve in salt or vice versa.
Are you going to record this last week?
Have I not? I am recording it, aren't I? Okay. February there. I'm getting old and kind of senile, so. And I recorded that too. Okay. Just so we know the two different kinds there, okay? So solution versus, okay, mechanical mixture, okay? In a mechanical mixture, you can obviously see both parts. So the one on the left here, okay, that's a solution or a homogeneous mixture, okay? This is a heterogeneous mixture or mechanical mixture because those things, I can suspend one in the other, but I can't get it to dissolve. All right, questions on those terms? Okay. Okay, now solute is the substance that is being dissolved. Okay, so if we're making coffee and you're adding creamer and you're adding sugar or whatever, you know, if you're having your double, okay, all of that stuff is a solute. You're getting it to dissolve in the water. Okay, even to an extent, the coffee is a solution. Okay, as you run the hot water through the grounds, okay, some of the grounds dissolve. Okay, now do you still have some grounds at the bottom of the cup? That's the best swallow of the coffee, man. Okay, that's the good stuff at the bottom. Okay, if you've ever had like a Turkish coffee, that's like it's thick. It pours itself. Yeah, it's awesome. Okay, but that would be a mechanical mixture. That stuff didn't dissolve; it's solid particles. Okay, that's where all the caffeine is. Okay, that's the good stuff. All right. If we had a solvent is obviously the thing doing the dissolving, so most of the time that's going to be water. Okay, but sometimes water can't get stuff dissolved on its own, so we add things to it, which is why we call most of our cleaners like CLR, Mr. Clean, okay, those kind of things. Those are solvents, okay, we call them cleaning solvents because they help water to dissolve other things. Water is not going to dissolve soap scum and hard water scales from your shower by itself, no matter how much elbow grease you put into it, okay? So you need to have some other stuff in there to help you dissolve it and get it off of there. Okay, everybody all right with those terms? Okay. Okay, so precipitate. Any solid that's produced in a reaction and will not dissolve into solution. Okay, I'm going to show you just a quick video of what that looks like here in a second. Okay, you can see the picture here. We've got the precipitate at the bottom. That is not a puddle of vomit at the bottom. I'll talk about what that is. I'm sure. Okay. All right. So, in terms of solubility, precipitates, etc., okay, you kind of see how this works. All right. Now, solubility is obviously the degree to which something will dissolve in something else. Not everything has the same solubility, and solubility can be affected by environmental factors, like temperature is the number one. Okay. What else can affect solubility? Yeah, agitation. Okay, the more you get it moving, okay, the better things can get into solution. Okay, those are kind of the biggest ones, but actually atmospheric pressure can also affect that. Okay, how soluble something is, especially if you're talking about the solubility of gases, okay, because gases can be soluble in other materials, even in liquids. Okay, like for example, if you drink any carbonated beverage, okay, then you've got carbon dioxide that's in the water, okay, it's dissolved in there, and eventually it comes out. Okay, so why the can cracks, okay, when you open it up. Okay, now the picture you have here. Some things should be soluble. Some things shouldn't be. Okay, the modern Twinkie is water soluble. The original Twinkie was not. Why? What have they changed about the Twinkie, Peter?
You gonna guess trans fat?
It's something to do with some of the fats they have used, yes. Okay? Basically, the original Twinkie was real cake with like a butter icing kind of filling inside. Okay? Real cake is made with eggs and flour and butter and sugar, okay, and all of those kind of things. Well, butter is not soluble in water. Okay? Your eggs are also not water soluble. Okay? So those things would give the cake a certain texture and certain color. Okay? Twinkie is yellow, at least the original Twinkie was yellow, because it had eggs in it and no other colorings. Okay? That color was the result of having eggs in the batter. The modern Twinkie does not have eggs. It does not have butter. Okay? It has different substituted oils. Okay? reconstituted like amalgam, which is used in replacement of eggs. Okay? All of these materials that result in a slightly different taste, but for the most part a similar taste and texture to the original, but bacteria don't grow on them. So the shelf life of a modern Twinkie is far longer than the shelf life of an original Twinkie, which was, after all, just cake and contained milk and butter and things that could sour and spoil. Okay? So the modern Twinkie can sit on the shelf for months. Okay? Not only because of what it's made out of, but because of the things they add to it. And I'm not one of those people that's like, ooh, I gotta eat all organic stuff, because I totally don't do that. Okay? But what I'm saying is, we do add things to our food in order to keep them from spoiling. We call those what? Preservatives. Okay? Some of them are the same things that are used in mortician's fluid. Here's a pleasant thought for you. Okay? It's what they put into cadavers. Yeah, corpses, so that they don't get smelly before the funeral. Okay? Yeah, mortician's fluid keeps things from breaking down, okay? And prevents the growth of bacteria and fungus. Well, it does the same thing on your food. In small amounts, it's not going to kill you. Okay? Are you eating a dozen Twinkies a day? Well, I don't know which would kill you first, what's in the Twinkie or the fact that you're eating that much fat and crap every day. But, okay? Certainly wouldn't be good for you. Okay? But the modern Twinkie, because it doesn't have eggs in it, also has to have yellow dye number 5 added to it. Okay? You can't get Twinkies in lots of countries in the world because yellow dye number 5 is a known carcinogen. It means it causes cancer. Okay? It's still allowed here, okay? Because again, as long as you're not eating 10 Twinkies a day, everything in small amounts is not going to kill you, right? But these are all things that are water soluble. So you put a Twinkie in water and it's pretty much all of it is going to effectively dissolve and become that. Okay? Whereas if you put a piece of cake that you've made at home yourself from scratch in, it's just going to be like a sponge, right? And it'll just soak up the water, but it won't dissolve. It'll get squishy. Okay? But a Twinkie, most of it now will dissolve, okay? Because it's got all these ingredients in it that are water soluble, okay? As opposed to fat soluble. Okay, there's a pleasant thought for you. All right, let's talk about this solubility chart. The one I have up here is slightly different than the one you have, but it still works pretty much the same way. Okay? This chart will allow you to determine what is soluble and what is not. Now you're probably going, so what's the big deal about that? Well, when you have chemical reactions happen and precipitates are formed, it's important to be able to know which is the precipitate. Okay? So if I have a reaction like this one, okay, this is one we'll actually do later. Okay, if I mix potassium iodide with lead 2 nitrate, okay, my products after the reaction are going to be potassium nitrate and lead 2 iodide. Okay, when this reaction starts, okay, potassium iodide is a clear solution. Lead 2 nitrate is a fairly clear solution with a slight grayish tint to it. Okay? When I mix these two things together, I get a white solid, a lot of it, and a clear solution on top. Now, would it be important for me to know which one of these two compounds is the yellow precipitate and which one is the solution? Yes. Okay, that's where my solubility chart comes in. Okay, I can use my solubility chart to determine if the solution is potassium nitrate or lead 2 iodide. Okay, and I do that by simply looking here. So my two compounds were potassium nitrate and lead 2 iodide. So here's what I do. Okay, I look up the non-metal, okay, on the top row. I can see that nitrate is right here. Okay, and it says that nitrate is very soluble with most things. Yay. Nothing like seeing most as a clear, definitive answer. Okay. But luckily, it lists down below the things it's basically not soluble with. Okay, so slightly soluble because everything is slightly soluble. Okay, we basically say insoluble. Okay, so if nitrate was with this stuff, this stuff, this stuff, or this stuff, it would be a precipitate. Well, I don't see potassium there, so is potassium considered to be part of most? Yes, it is. Okay, that means that this stuff is soluble, right? So it's probably not my yellow precipitate from the reaction, right? Now let's check with this. I've got lead 2 iodide, so I go on my chart and I find iodine. Once again, soluble with most things. Thanks, that's helpful. Okay, I go down here. It says it's not soluble if it's with copper, silver, mercury, mercury 2, okay, and lead 2 plus. Okay, this is iodine with lead 2. So this stuff is soluble or not? Not soluble. So this is my yellow precipitate. Okay, that's how my solubility chart works. I look up my non-metal. If what it's with is in the first row, it's soluble. If what it's with is in the second row, it's not soluble. Simple as that. Okay? All right. I want you to try, well, let's just do these two first. Okay? Let's figure out whether iron 2 sulfide is soluble or not. So I find sulfide. Okay? Sulfide's right here. It says it's soluble with iron, sodium, potassium, ammonium, lithium, magnesium, and calcium. Well, I don't see iron listed there. So is that stuff soluble or not? It's not soluble. Okay, and then sodium hydroxide. So if I find hydroxide, it's right here. It says, oh, there it is. It's in the first row, so this stuff is soluble. Okay. If the metal it's with is in the first row, it's soluble. If the metal it's with is in the second row, it's not soluble. Okay, I want you to try those 8 right there. Okay, just write soluble or not soluble. Okay. I think all of those are in the For lithium fluoride, I look up. Fluorine is right here, says it's soluble with most things, but first thing listed down in the slightly soluble or not soluble row is lithium. All right, so that stuff is not soluble. Okay, for number 2, we got sodium sulfate. Okay, so if we find sulfates right here, it says soluble with most things, but not with these. Okay, sodium is not listed in that row, so that one is soluble. Okay, number 3 we couldn't do because it was sulfide and we didn't have, or sorry, it was ammonium nitrate. We didn't have that on there. Okay, so silver chloride. So if I go up here to chlorine, soluble with most things, but silver is listed down here in the not soluble row. Okay, so that one is not soluble. Okay, for number 5, lead 2 iodide. We just talked about that one. It's not soluble. It's a yellow precipitate. Okay. For number 7, we got potassium phosphates. Okay, so we're looking at phosphate right here, soluble with potassium, listed right there, so that one is soluble. Okay, and lastly, we've got mercury 2 chloride. Okay, so here's chlorine right here. We go down into that row, and we can see that mercury 2 plus is listed right here. Right, so that one is definitely not soluble. Alright, does that chart make sense? Alright, because you will definitely be asked to do that probably on your next quiz, but also when we get to our reactions lab and we have to identify which things are precipitates in that lab report. Okay? That's what we'll be using that for. Okay, any questions on solubility? Alright, then we're going to move on to polar nature of water here. Now, when we talked about molecular compounds back at the beginning of the unit, okay, we said that they share their electrons, and that's true. What we didn't say was how well they share. Okay, like I know like my 2 kids, they share that stuff, and sharing does not mean apparently to them that they both get it in equal amount. Okay, well the same is true for polar molecules. Okay, they do not share the electrons equally. Some things hold on to electrons more tightly than others, which means they have them more often. Okay, so when we're looking at water, for example, okay, water is made up of 2 hydrogens and 1 oxygen. The part of an atom that tells us how well it holds on to electrons is called its electronegativity. It's one of the things that's actually listed in each element's box on your periodic table. Okay? Not something we'll ever use, okay? At least not in Science 10, you'll use it in 10, 20, 10, 30. Okay? You can see electronegativity is listed right above the symbol. Okay? For iron, it's 1.8. For oxygen, it's 3.4, which is really high. Okay? And for hydrogen, it's 2.2, which is kind of average. Okay? So what that means is oxygen holds onto electrons far more tightly than does hydrogen. So when they're in a compound together, the electrons they're sharing spend more time with oxygen than they spend with hydrogen. So rather than seeing this electron here, okay, that actually belongs to hydrogen doing this and going around these two things equally, it actually does more of this. And spends way more time around the oxygen atom than it does around the hydrogen atom. Okay? What that ends up doing is causing one end of this molecule to become negatively charged and the other end of it to become kind of positively charged. Okay? So the electrons hang out down here. They don't even really get above the nucleus of the hydrogen atom, and the nucleus of a hydrogen atom just contains what? One proton. That's it. Okay? So the most positive thing there is, that's all that's in the hydrogen atoms, one proton. Okay? So there's the hydrogen atom, there's the protons. Okay? They're on the top and they're kind of exposed. Okay? So there's these two positive charges that are just sticking up out of the top of the molecule. Meanwhile, all the electrons hang out down here around the bigger oxygen atom's nucleus, okay, and make the bottom of the atom more negatively charged. Okay? So that's why we call it polar. It actually has two positive poles and two negative poles. Okay? Because the electrons from hydrogen end up kind of pushing the electrons from oxygen down this way, so we get these negative charges down here. Now, do you ever have just one water molecule hanging out by itself? No. So if there are other water molecules around, they can get attracted to the other parts of other water molecules. So if there's another water molecule right here, okay, its negative end or pole can be attracted to the positive pole of another water molecule. And they can actually form a weak hydrogen bond between the two. Okay? Now hydrogen bonds form and break and reform and break and reform and break all the time. Okay? They're not very strong, okay? But they can form and break and reform very easily. This is what causes surface tension. Okay? Is the bonding of one water molecule to another via a hydrogen bond. Okay? It's not a chemical bond, there's no reaction there, but they stick to each other and form that meniscus, that surface tension.
That's why it's so easy to break that meniscus.
Exactly, that's why it's so easy to break the meniscus, because they're very weak bonds, right? And why, you can only get beads of water on the side of a glass to get so big before they slide down the side of the glass. Right? They're just, that force of hydrogen bonding is only so strong. It's strong enough to do the things that plants and animals have evolved to do using it, but beyond that, it isn't very strong. Okay, so the big thing to know here, guys, about polar molecules is that electrons are not shared equally. Okay, so the sharing is not equal. Some elements are more electronegative than others. That's what we just talked about. Okay, and as a result of that, we get these poles where molecules can form hydrogen bonds to themselves. Okay, or to ones that are like themselves. Okay, and water can form hydrogen bonds with other materials, okay, like glass. Okay, and that's what can cause water to stick to the side of a glass, okay, in that situation. Okay, so the bonds where the electrons are not shared equally, we call polar covalent bonds. Right, because there's still a sharing. That's what covalent means, sharing. But because it's not equal and they spend time at different ends, it's polar. All right, now this is where you can kind of see what would happen as water starts to contract. Okay, if we start pushing these water molecules together, the positive ends start getting closer to each other, the negative ends start getting closer to each other, and there'll be a kind of a rebound effect that will cause the water to expand right before freezing. Okay? So one water molecule can actually form 4 hydrogen bonds. Okay? So it can bond to 4 other water molecules or 4 other polar molecules of whatever kind. Okay? So it's shaped that way. Okay? It's shaped like a right angle like this because of the repulsion between these two protons, and between the 2 hydrogen atoms. Okay? And this again is what causes these anomalous properties. So liquid water actually has the particles closer together than in ice. Okay? So in ice, the hydrogen bonds are still there, but we get that crystalline kind of structure of ice. Okay? But the crystalline structure of ice is quite random. It just happens to be kind of wherever the particles go at that moment of transition from liquid to solid, right? Which is why no 2 snowflakes are the same, okay? Because it's a completely random process that produces that crystallization and the ordering of the molecules and basically decides on the crystalline structure. Now, are there 2 snowflakes that are the same? Probably. Okay, but if you have a whole bunch of them together, they all look a bit different. Okay. All right. It also means, if we can see the spaces between the water molecules here, that ice is obviously less dense than liquid water, so ice floats, which is not the case for most solids. Okay. If you have a chunk of solid like lead, and you dropped it into molten lead, it would sink to the bottom. Okay. You would not have a lead cube. Okay. It would float, okay, in its liquid counterpart. Okay. Basically everything else sinks and is more dense as a solid. All right, so the big thing to remember here, hydrogen bonds. If I'm asking you to explain what a polar molecule is, I'm going to want to hear things like unequal sharing of electrons. I'm going to want to hear hydrogen bonds, and then the 2 behaviors that hydrogen bonding can produce, and that's what we're going to talk about next. Okay, so hydrogen bonds, okay, cause polar molecules to be able to stick to other things. All right, so in a plant, especially a tall tree, water has to be transported from the roots to the leaves. That can be, in a really tall tree, over 100 meters. Okay? The plant expends no energy to do it. Okay? Plants use no energy to transport water from below ground to the top of their leaves. Okay? What they use is the properties of water to do it. So as water evaporates out of the leaves, goes into a vaporous form, it's hydrogen bonded to liquid water molecules below it. So as it leaves the leaf, it actually pulls on the water molecules below it because they're all hydrogen bonded together. Okay? How many people ever played with like the barrel of monkeys when you were a kid, right? And you could link all the arms together and you could pick a whole bunch of them up. That's what the inside of the tubes of a tree or any other plant look like. If you could see all the water molecules, they'd all be hooked together like that. When you pull on one, you pull on all of them. Okay? And they all come up. All right? So there's hydrogen bonds between the water molecules, and there's hydrogen bonds between the water molecules and the inside of the tubes. Okay? They're strong enough to hold that really small column of water from falling back down. The key is the tubes have to be microscopic. Okay? So the tubes that a plant uses to transport water are only a few micrometers across. Okay? It's not like a straw. Okay? You ever notice that it's really easy to draw like pop or water through a really thin straw as opposed to a really thick one? Okay? Like we use thick straws for Slurpees because Slurpees have the extra added support of their being partially frozen and stuck to each other. Okay? But the bigger the girth of a straw, the harder it is to pull water through it because you're supporting a lot of weight. The column of water weighs a lot, and the water molecules can bond to each other but not to the sides of the straw because there's only so much surface area that they can touch. So you got this big unsupported column of water in the middle that just can't be held up. Whereas if the tubes are microscopic, the water molecules can bond to the sides, to each other, and they're all supported, and it can hold it up, and it won't fall back down. Okay? Does that sort of make sense? So even though it's not a very strong bond, it's strong enough for plants to take advantage of. Okay? So the behaviors we see are in this picture right here. Okay? Adhesion is a hydrogen bond to another material. Okay, what we call adhesives, like glue is an adhesive because it glues things that are not alike together. Okay, so adhesion means water bonds via a hydrogen bond to something else. Okay, and there's cohesion. That's a hydrogen bond between two water molecules. So those two processes go on inside the stem of the plant and allow the column of water to be supported and drawn up the plant. Okay, everybody all right with that? Okay, would that be a good example to use if I was asking you for an example of a living organism that uses the polar nature of water?
Yes.
Definitely. Okay, so that's what you're going to need to be able to explain to me. I always ask a question on a unit exam about explaining what a polar molecule is. So a molecular compound where electrons are not shared equally that can form hydrogen bonds with each other because of its charged ends, cohesion, adhesion. Okay, I always ask a question about that stuff. Okay, so we got cohesion here, okay, due to hydrogen bonding between water and other materials, or sorry, water in itself, okay, and then adhesion was water to other things. Right, so hydrogen bonds can cause water leaving the veins in a leaf to tug on the molecules farther down, and the upward pull, okay, is transmitted along the vessel all the way to the roots. Okay, adhesion is the clinging of a substance to another, also plays a role because water can adhere to the cell walls of the vessels, preventing it from falling down. Okay, and that's okay. So we can see surface tension here. I've never been able to do this, but apparently you can. I spent an afternoon wasted an afternoon trying to do this, and I couldn't make it work. Okay, but apparently you can balance a paperclip on the meniscus of a glass of water. Okay, there's enough surface tension if you do it right. I never got it to work. Okay, and you get, like in the morning, sometimes you see dew on the leaf of a plant. Okay, the reason for that is the leaf of a plant is covered in a waxy cuticle, which is also a polar molecule. Okay, and so the water can adhere to that and form these big beads which have their own surface tension until they get either too big or something jostles the leaf, and then the water will run off. Okay, so plants actually don't absorb water through their leaves. Okay, it actually sits on the leaf and doesn't penetrate. Okay, but it can run off and then be on the ground where their roots are. Okay, so all examples of water being a polar molecule. Okay, and even animals will utilize the fact that water is a polar molecule. If you've ever seen the Jesus lizard, okay, it can kind of run across small bodies of water. Okay, it has that like weird kind of running gait where it looks like its arms and legs are just going in circles. Okay, because it can move quickly enough, even though it does break the surface tension, it's moving quickly enough that it's setting its next foot down before it kind of falls in, right? And it can actually run across using that surface tension. And lots of small bugs that you see sitting on the surface of the water are utilizing the surface tension of the water to stay afloat. Okay, if you've ever done any fly fishing, the same idea is used to keep a fly on top of the water. Okay, it sits in the surface film or on the surface tension and doesn't sink. Okay, could you get this thing to sink? Yeah. How? Throw a rock beside it. You'll break the surface tension. Okay, and it'll sink. Okay. Anything that'll break the surface tension. Okay, like think about where it's easier to skip a rock. On a still lake or a moving river? Yeah, on a lake, right? When you skip a rock, you're bouncing it off the surface tension of the water. Okay, but if the surface tension of the water is already broken because the water's flowing over rocks already, you're not going to be able to skip the rock. Okay, it's way easier to skip a rock on a lake than it is on a flowing stream. All right. Okay, we're going to leave it at that. You got about another 10 minutes here. If you want to get together with your group and talk some more about your analysis for your lab, figuring out which compound is which, now would be a good time to do that.